This UCSD TV program is a presentation of University of California Television for educational and non-commercial use only.
Good evening. My name is Nigella Hilgarth, and it's my great pleasure to introduce our speaker tonight, Dr. John Orcutt. John Orcutt is a distinguished professor of geophysics at the Scripps Institution of Oceanography, University of California, San Diego. He's also a distinguished scholar at the San Diego Supercomputer Center, and he directs the National Science Foundation Ocean Observatories Initiative, CyberInfrastructure, which is the implementing organization through CalIT2, which is on the campus of UC California, San Diego. John earned his bachelor's degree in mathematics and physics from the US Naval Academy and his master's from the University of Liverpool, and he received his PhD in geophysics here at Scripps Institution of Oceanography. I could spend the rest of the evening and allow him no time to talk to tell you about his incredibly distinguished achievements in academia and in administration. He has given incredible service nationally to science, and his list of awards and medals is extremely long and extremely distinguished. So I think what you really need to know about John is that we are very lucky tonight to have such a distinguished administrator and scientist who is so knowledgeable about the future of oceanography and about ocean observing systems come and talk to us tonight. So John, thank you very much.
This is a building on the campus of the University of East Anglia, northeast of London, and it's the Climate Research Unit, which does climate work. You may have heard about it in the recent past. Something happened there recently that I found to be very interesting for science and very interesting for what I do. And it referred to in this as an incident here in which about 160 megabytes of data, 1,000 emails, and 3,000 documents were downloaded without permission and made available a little bit later on a website which, if you ever are interested in climate, Real Climate is a great website to tell you how climate actually works and so on. But a hacker posted these what amounts to emails on Real Climate, and they were downloaded everywhere. People read them, and it then became known as Climategate, and you probably remember that.
Political storm over global warming. Skeptics claim that emails hacked from a leading British research center prove that climate change data was manipulated and that global warming is in fact not happening at all. Well, the news did get a lot of people a little more confused about what the truth really might be, so we asked Pulitzer Prize-winning author Tom Friedman for some answers. Take a look. Give me your take on this scandal, if we can call it that, and what it has done to the credibility of the environmental movement overall.
Well, these were hacked emails from one of the important climate research centers over in the UK. And frankly, Campbell, as someone who follows this issue, cares about it, I found some of those emails disappointing, frankly, in the kind of way in which it seemed that they were trying to keep certain research out, of the discussion. Because I think transparency here is everything. Okay, you say this, I say that. Here's my data. Here's your data. That said, okay. To me, we have to understand, the whole climate change issue. The climate is the most complex system you can possibly imagine. But what do we know? What does your viewer want to know when they think about it? We know that the Earth is enveloped, okay, by a greenhouse gas blanket. That's what actually creates this greenhouse effect, that we have a nice warm Earth. even though, you know, it's freezing out there, as you know, when you go up in a spaceship and scientists. But here's my take on it. Maybe it isn't 90% like some of the skeptics say. Maybe it's only 80%. Maybe it's 50%. But you know what that means? There's a 50% chance that when you put that CO2 in the atmosphere, it stays there for about 3,000 years. So if we keep putting it there, and it stays there for 3,000 years, and it does start raising temperatures, it's going to be hot here, Campbell, for a long, long time. So to me,
the bottom line
is that the risk is still there. They say it's only, what if they said it's just a 10% chance? What if I told you there's a 10% chance if you keep smoking, you're going to die of cancer?
Still reason enough to quit smoking.
Exactly right.
Right.
And so, and this ain't 10%. This is a lot higher. So that's kind of how I deal with it.
Well, that was the first segment of this, and it was Tom Friedman. The introduction was one of the more interesting parts of this, in which the person asking the questions was saying that we understand that really climate change is not occurring as a result of man's introduction. It's all a hoax. And Tom providing a fairly reasonable presentation then of climate science. So then we'll go to another one. And I'll turn my volume off again.
Back to our top story, a huge global warming conference about to begin in Copenhagen right now. Lots of serious views underway, serious debate unfolding. Let's get Oklahoma Republican Senator James Inhofe. He's joining us in Massachusetts. Democratic Congressman Ed Markey. They strongly disagree on what's going on. Senator Inhofe, let me start with you, because the EPA Administrator, Lisa Jackson, today she said this in announcing the steps that the Obama administration wants to advance.
There is nothing in the hacked emails that undermines the science upon which this decision is based.
Is she right?
Oh, no, she's not right. You know, we had Lisa Jackson before my committee, not more than a week, maybe a week and a half ago. And she said that, you know, that they relied upon the IPCC for the science that came to this, decision to have the endangerment finding. And actually, I have a letter from her in writing saying that's where they get their science. Now we see that that science has been pretty well debunked. And one thing interesting about this, Wolf, is that I remember a long time ago on your program, 4 years ago, I made a speech on the Senate floor where I talked about all these scientists coming in, talking about how they can't get their side on there, and the science is all rigged. And so I gave a speech on the floor. It lasted about an hour. And sure enough, what is happening today in this whole debate is just what we said was happening 4 years ago.
Well, let me let Congressman Markey weigh in. How much damage do these leaked emails do to your side
at all?
Of this story?
In fact, the important thing to keep in mind here is that the National Academy of Sciences of every country in the world has endorsed these findings. It's not just the United States. It's not just the British. It's every country in the world. And in addition, and this is something that the skeptics, the deniers, cannot overcome. We are reporting this year the warmest ocean temperature in history. The last 9 years have been amongst the top 10 warmest in the history of the planet. There has been a 6-degree increase in temperatures in Alaska over the last 50 years, which is what's leading to villages actually falling into the ocean with the melting of the permafrost. So the fundamental science has not been altered at all by this.
I want Senator, hold on one second. I want Senator Inhofe to respond, but on the specific question of these scientists trying to prevent Congressman Markey, trying to prevent some dissenting scientific views from getting some air, from being known, you condemn that, don't you?
Well, absolutely. But remember, almost all of the criticism that was in those emails was in fact included in the Intergovernmental Panel on Climate Change that the United Nations released. So it wasn't as though all of this skepticism wasn't in fact identified. It was only that the overwhelming majority of scientists in the world, thousands of them, rejected the conclusions of this handful of skeptics.
Hey, Ed, you're in denial. You don't understand what just happened. This is a very serious thing. Let me just tell you, I want to read two things, Wolf. One is from the Atlantic Monthly. The stink of intellectual corruption is overpowering. And then this is the big one. The big publication in UK is the UK Telegraph. This is the worst scientific scandal of our generation. You can't play this one down. This is a huge, huge deal. And the fact that they are going into an endangerment finding using this as the science, that makes it that much worse. It's a recognition that we have won and they have lost in terms of a legislative a cure for this. Your bill is dead. It's not going to go anywhere. The Boxer bill is dead. And for that reason, in order to save face at the big meeting that is watching us right now in Copenhagen.
That's a little harder for scientists usually to hear that. There was a lot of criticism of the emails. People are generally, I think everybody's familiar with emails, and you sometimes make use of emails in a way that you probably, in retrospect, shouldn't. But you do build up an archive of back and forth, and these were some of the comments that people actually said, and that were in these on these notes. You know, I just completed Mike's nature trick. You've heard this one, I suspect. The trick of dealing with the data and what it actually means is that for the last couple of decades, the quality of the data have become good enough that using good instrumental records was better than using the earlier and older proxies that were available, like tree rings and so on, to estimate what the temperature was during the year. And so we now have instruments for obviously measuring temperature and doing it reasonably well. Here's a ding on the Journal of Climate Research by Michael Mann, cautioning don't leave data around because somebody might take it off. This one's a good one, saying that natural variability is not an explanation for the fact that temperatures during the last couple of years have actually decreased some. And he goes on about the fact that we can't account for this lack of warming at the moment is a travesty. And it shouldn't exist. And what he was really talking about in this particular case is our observational systems on the face of Earth are not adequate to actually understand the system well enough to make the measurements necessary to know what is happening on shorter time intervals of a year or so. So he was advocating a better observing system, not saying that there wasn't an issue with climate and the anthropogenic effects of the buildup of greenhouse gases. So one of the lessons to be learned in in this particular scandal, as it were, Climategate, is that data need to be open. There are a lot of organizations in the world. There are several European countries, a number of Asian countries, which won't make data available. For example, their atmospheric temperature, winds, and so on, that they ask that it be bought. And the idea is that by doing that, by paying for it, you'll help them support the collection of those data. The data generally aren't, in most cases, available, and so collections are made, waivers are received for scientific uses of data. But by binding those data in, the data then have a characteristic of not being very open or available. So one of the things we have to do with any kind of a modern future observing system is make sure that the data are open to everybody and anybody that wants to use them, so that climate skeptics, scientists, laymen can go in, farm data, have a look at the data, think about this themselves, and understand it. Kids can do school projects, science fairs, and so on these data. And the observing system that I'm currently building with a team that I'll talk about more a little later. This is one of our main goals for that program. And the other is provenance, and usually you think of provenance in terms of art. Where did the art, some art, you have a trace that goes back a century or more centuries into the past, in which you can demonstrate, hopefully, that the piece of art that you own or bought actually was painted by the original artist. Or a good bottle of wine that was ostensibly bottled by Thomas Jefferson is in fact worth that money, which it turns out In a recent case, the Provenance wasn't much good in that particular case for those bottles of wine. They really weren't Thomas Jefferson's, and it would be pretty old stuff, even though it might have been pretty hardy anyway. But provenance for data is critical in understanding climate. The original data collected, and usually they come out of the field or over the internet in terms of volts from some sensor or some instrument, and that has to be converted into engineering units like temperature or wind speed and so on. There's a conversion process, and scientists and engineers, being people, oddly enough, make mistakes. And 5 years later, you will find a mistake in the way you interpreted and converted those data, and you have to go back and do the whole series over again. But you want to have the new series available, but you also want to tell people that have used it in the past what was done to change it from the original version to the next version and so on. And that's easy to do today because the data storage is so inexpensive. Every time you modify a data set, a digital data set, you just make another version of it and store it in addition to the original version. So you never give away the original version, but you describe from step to step how you change that, so that a scientist coming along 100 years from now will be able to go back and establish how those data actually grew up. So those are two important aspects. And this just shows you, and speaking of temperature, this shows from the middle of the 19th century to present day what the temperature looks like. It's about 1 degree centigrade warming. You see there's an awful lot of noise and variability, and it goes up and down, but in general it's a general trend in this direction. Sea level is a really interesting one, because back here in the 50s up into the 90s, really, these were measured with tide gauges around the world. And there are a lot of errors that creep in when you do that. And the most recent part, which you can just see in red here, is all done by satellite quite frequently, several times a week. And one of the things you see is the accuracy is getting better, and the rate at which that sea level is increasing is going up. Snow cover, you can see, is generally going down, and we sense that in California with the early melting of the snowpacks and so on here. That's going to create a problem for us with water. And if you ask any person that lives in Venice and has lived there for 3 or 4 decades, you'll know that they understand global warming is a big deal, and lots of steps are being taken to engineer against that, a thing in which a lot of people from Scripps and MIT have been involved over the years. This is a shorter time period going back to zero here, birth of Christ, and onward here to the present day. This is the thing that's called the medieval warm period. And then the little ice age here, the warm period is about 1000. The ice age extends up here to almost 1600. But then more recently, this has begun to warm rather more quickly. And this is as much as you see, I think, in most temperature data, which are not particularly easy to deal with over long periods of time. And there's a lot of variability in it. It's the kind of thing that's referred to as a hockey stick. But the real hockey sticks are in the greenhouse gases. This is carbon dioxide, methane, nitrous oxide. This goes back 10,000 years from the present time, and you can see these patterns here of the introduction of a large amount of CO2 in the atmosphere during the industrial period here, methane as well from agriculture, nitrous oxide in many cases from agriculture. So these are from the IPCC document, the last one, and show you proper hockey sticks and how will temperature vary in the presence of these increasing greenhouse gases is very likely to be in a very positive direction. So are we in a good position to really begin to understand how to measure these various parameters on Earth? Do we have the tools available? And that's one of the interesting things that I've been working with, are the integration factors that actually allow one to bring data from sensors in the field to the internet to people and for use in science and education and so on, in a really interesting place that I find to illustrate today's state of affairs is the Library of Congress. And this is the Library of Congress. Anybody that hasn't been there recently, this is the upper loge here. It's been refurbished and rebuilt in the last several years. And it's an absolutely gorgeous place. The marbles and the stone here, all these all the gold in this thing, the beautifully painted vaulted ceilings and so on. And the skylight in the rotunda, equally spectacular and gorgeous, and something that actually looks like a library then, with the carrels down below where scholars come in and check out books and so on, and have now for centuries. It's the world's largest library. It has more books, more holdings than anyone else on Earth does. And just to look at some numbers, the estimate is that there are about 25 so-called terabytes of data in the book collection. Not that all the books have been digitized, only a small number of them have. But if they were all converted to digits, it would be about 25 terabytes of books. Now, a terabyte is 25 with 12 zeros behind it, 25 trillion bytes. And because there's 8 bits in a byte, and bits, of course, are ones and zeros, there's 8 times this, or 200 trillion bits of information in the Library of Congress tied up in books. Today at UCSD and for this observatory network, I'm using a 10 gigabit per second network here, which if we divide this 200 trillion bytes by 10, what the hell number is that? 10, what number is that? 10 billion. It's really hard. I really don't like not using scientific notation, but anyway, if you divide these two out, you find the number of seconds, which is equivalent to 5 hours and 36 minutes. So it would be possible sitting here in UCSD to move everything that's held at the Library of Congress in 5 hours and 36 minutes, the largest collection of books on the planet. And that's only going to increase in the future. If we include film, images, and video in that collection, there's 120 bytes rather than 25, and we do the same silly calculation here, and you find that you could get the whole collection, everything, in 26 hours and 42 minutes. You could, in fact, then establish a Library of Congress pretty much anywhere you wanted it to be. Including here at UCSD and in La Jolla. And one of the things that I found in doing this, and people often don't think about this very much, is that Moore's Law is our friend. Now, you may not know what Moore's Law is, and many of you do, but I'm plotting here years down here and then sort of performance per dollar spent in an undescribed thing over here on the left. Computer density, which is actually Moore's Law, and its transistors per centimeter, square centimeter, is doubling in its size or density every 18 months. So every 18 months, you essentially double the computing capability on a chip, and you've seen that go up. My iPhone that I have here now is much, much larger than any computer I was using in the 80s. But this also applies, although it's not due specifically to Moore. Disk density has been going up, and this is bits per square centimeter that you can store on a disk drive. And this is going up with a 12-month doubling time. So every year, the density doubles, and that tells you why Apple's been so successful as long as the iPod has been around. Every year, the size of the iPod doubles in size, but the price actually stays the same or actually goes down a little bit. And that's Moore's Law in action here. It's just allowed them every year to have a new generation, if you will, of iPods, and people rush out and buy them. And that's now, nobody's buying iPods so much anymore, but they're buying iTouches, which is all solid state disk, nothing rotating in the system. But the real surprise here is optical fiber. And it has a doubling time of 6 to 9 months. I say right now, I started using 10 gigabits per second as an experimental device about 5 years ago. Now you can buy commercial products that manage 10 gigabits per second. And there are commercial systems that'll get you 50 gigabits per second. And in a few years, well, probably in a year or less, you'll be moving a terabit per second on that line. But even now, if you think of that as 10 gigabit per second speed that I use for the Library of Congress, that happens to be 20,000 times faster than the internet in my home from broadband service by Time Warner. And so sometime in the future, you've got a son or grandson, granddaughter that has a science project or a paper to write, ask them, why is it so different? Why is there such a difference between this system that's at the university and what's coming into my home? It's kind of a really interesting cultural, political, business question, of course. But one could be having much more access than we are. So I'm running this thing. I'm building what the NSF calls CyberInfrastructure for the observing program. And we have systems located around the planet here, which we are sending around the U.S. on these optical fibers to provide services for science, education, and the public in general, and using very high bandwidth networks. These are some of the 40 gigabit per second to 1 terabit per second networks that are are available in the U.S. right now. And this is what it looks like globally a year ago. I haven't run the newest one, but you see the U.S. is heavily covered with 10 gigabit per second capabilities. We have reaches over to Europe, quite a lot of distribution there, to Asia and to Australia, but there's there's a connection here to South America, but Russia, except up here, this one connection in all of Africa, doesn't have access to this kind of capability yet. And you can still see the technology for this kind of thing is concentrated, at least for the moment, in the United States. I'm running this program right here. It has a construction period of 5 years. There's also a regional and coastal global system that's putting platforms in the water. Our job as in the cyber infrastructure is to integrate these and to go down, clear down to the sensor itself and bring the data from the sensor back into the system and available on the internet for anybody to use, and generally with what we call latencies of seconds. That is, from the time the thing is measured till the time it's available on your desk, it's on the order of a second's time, and that's what we hope to do. One of the things I found just to try it out with East Anglia is there is a data set that began back in the middle of the 17th century, actual measurements of temperature, instrumental measurements of temperature. It's the longest time series that exists for temperature or any other environmental element on Earth. But it's a collection of thermometers throughout a triangular area in the southwest of London, and the data are available, sort of, but you have to get permission to use it. And so I just tried signing on to see if I could get the data, and I did this last Thursday, and I still haven't got my email back saying how I can get the data. So this is not my goal. This is not the kind of thing I want to be able to do, and I think that everybody would like to be able to, if they have a question, just as you do now with Google, with a click, you could get those answers, you could get that stuff, whether it be the actual data or some product of that data that explains it for you. And so our goal is to move into this operations here area after 5 years in that state for at least the NSF plans to fund it for 25 to 30 years. And that's another important number, and I'll come back to it. This just shows some of the sites. This is in the Gulf of Alaska. This is the Erminger Sea south of Greenland. There are 2 sites in the Southern Ocean here in the Argentine Basin and in the Southern Ocean at very, very high latitudes. And these are buoys, and the telemetry in this case is by satellite, and the environments there, you can imagine, are pretty awful. Some of you have probably gone to sea in this part of the world, but you know characteristically the weather never ever is good. And it's always characterized by swells that are 10 to 15 meters and sometimes a lot bigger than that. It's a real thrill of a ride working down there, and we're going to be trying to make measurements of air-sea interactions and fluxes in that kind of environment. This is a cable network off Oregon and Washington that runs out to a mid-ocean ridge, and this is a 10 gigabit per second cable, and it also carries power out to run sensors and actuators, and then a line that comes up in the coastal area here toward Newport. This is the real high capacity system. It doesn't rely on satellite telemetry. The telemetry is high speed, 10 gigabits per second, as I said. So that's the physical layout. This is a thing called the Major Research Equipment and Facilities Construction Program, MREFC, and it's a $400 million program from the NSF for 5 years of construction, and that's unusual for the NSF. I mean, I remember not many years ago, my biggest grant from the NSF was about $100,000, and that would last 3 or 4 years and several times at sea. And so this sort of outweighs that. But with that comes a lot of conditions, of course, and I'll talk briefly about that here. But the cyber infrastructure part is funded a little less than $10 million a year for this next 7 years. And the US, in fact, I think no one in the world has made that kind of investment previously in actually integrating data from the environment to bring it to people for their use, be they scientists, be they students, be they interested people, policymakers, and so on. So for me, it represents an incredible opportunity that I've never seen. I have a 7-year cooperative agreement, it's called, with the NSF now to work and build this thing, test it, and put it in place during the next 7 years. And I'm really looking forward to doing that. It's a great for me and for, I hope, everybody that works with me on this. It's a real opportunity. And speaking of that, this is dull as toothpaste, but this is the org chart. Everything has to have an org chart, and this is me and my deputy up here. And we have, this is the engineering and administrative team. We have people here from UCSD, but we have a fellow from Raytheon. The project scientist is from Rutgers. Cheryl Peach, who is here tonight and helped me get set up, is the manager for education and public engagement for the program. Kruger here is a professor at the Computer Sciences Department. And Matt Arrett is a person that we hired, and he's the program manager who looks after the senior architect, the development manager, and the to-be-named operations manager at UCSD. And then this layer here are the integration teams at UCSD. And altogether, this year, we're hiring about 40 new people at UCSD and in the area, scientists, engineers, particularly programmers who will immediately become taxpayers, which is always a good thing to have happen these days in California. So I'm trying to do my bit here by, in this recovery business, by hiring some folks and keeping them employed successfully. If you look down here, there's, for all of our major systems down here, the common operating infrastructure, the sensing, acquisition, data management, and so on, we have people from varieties of places like the National Center for Supercomputer Applications, Red Hat Linux. I showed you we had a fellow up here from Raytheon, University of Chicago, MIT, Woods Hole, I think then JPL. JPL is the group that's working with us on the interactive part of this. They also, that team works for the Earth Observation Satellite group on scheduling and managing the satellite. And we're basically have them on our team because we've simply moved the kind of stuff they have for managing that satellite into the thing that manages our observatory, and schedules change. And this is the team. We had a beginning kickoff meeting in August in Colorado, where I actually grew up, but this shows you some of the people physically. These are basically new people involved in working on this. This is the program manager here. There's Cheryl Peach. You'll recognize her this evening, myself. But we had a very good group get together here to kick off the construction period for this program. And one of the things we have to do, and this is the reason for this, as I said, systems engineering has become a big deal for us. And we have for something for $400 million, you get to spend a lot of time working on requirements break down structures and so on. And this is me, I guess, the pointy-haired guy. He's the one speaking, and he says, let's schedule a scenario-based roundtable discussion about enterprise project management. Could substitute OI. We use our infrastructure survey tool to architect a risk-based tiering system, and the two engineers or programmers behind him said, that almost meant something. And I'm tempted to stop acting randomly. So this is me, the pointy-haired guy, and I can speak systems engineering now with the very best of them, and occasionally even understand it well. So how are we different? A couple things I mentioned already is open access to data. There are no proprietary periods for holding the data up. We have to address provenance to develop scientific trust here, but other things we're doing is bringing data back. I mentioned that in near real time with latencies of seconds. And it's an interactive network, and I'll show you what that means briefly. And we want to connect science to educational and social networks. So what do data look like today? This is the way scientists generally work today. In fact, most everyone does. We have engineers largely who build systems and go out to sea or on land, and they make observations. And the data come back in tapes or by the internet, and they're put away in a library somewhere in a bunch of files. And then at some undetermined time later, some scientists will show up and engineers, and they will analyze the data. So they suck the files out of this system here maybe years later and actually try to understand what was going on at that previous time. And generally the people that do stuff out here are different than the people that do stuff here, and neither side generally in science likes the other one. So there's always these huge battles. Faculty meetings are awful in that sense here. So this is the way it works today. This is a bit different. We still have to observe things. But then we immediately move that data that are arriving in real time into analysis techniques, finding things that are happening in the Earth, or putting them in models, running models to predict the future state of Earth, or just to interpolate between the measurements and understand what's going on. And invariably we find there are holes in the data that we don't have. And so we use that knowledge then to interact again with the observatory. The observatory can be changed and modified based on the measurements that already made, and this is a unique part about this program that we're running. This thing can be closed in a loop here so that it operates on a machine-to-machine basis, and sometimes a human will get in the loop, but you get worn out quickly being in that loop, and so it's not something you do always, but you create not just data but knowledge about the environment as you do that. But it does allow you to command, for example, autonomous vehicles that are working at sea to collect data to fill in these holes is one of the good uses for that data. Well, there is an elephant in the room in all this. There are probably several elephants. There's probably a herd, but it's all I could get in the top of my GPP. But this, Susan Solomon said it very well. She's at NOAA, a very well-known climate scientist. People have imagined that we stopped emitting carbon dioxide, that the climate would go back to normal in 100 or 200 years. What we're showing here is it's not right. It's essentially an irreversible change that will last for more than 1,000 years. So what we're doing and thinking about right now, and I'm standing up here talking about building a system to integrate observations, I'm really talking about the system that's going to reach well into the future and has the capacity. Doing things just well enough to make it work right now is not good enough anymore. It's got to work, and you have to think very hard about how you put this thing together, or you'll never be able to afford in the long term the operation and maintenance of a system like this. And it will change. That thing I showed you before, the systems engineering requires continuously during this process, even when you've built it and are operating it for the next 30 years, which the NSF has given us to work, you still have to think about all the changes you have to make, and nothing moves faster than networks and computing speeds and even the algorithms and the way you do things, and all that has to be integrated, or if you don't, you get 3 or 4 years behind. It then becomes so expensive you can't even dream of beginning to maintain something like this for that period of time. So that's the elephant in the room. I think people don't think about that, you know, climate is changing, we have to do something about it. But even in our memories, even, you know, people won't even know who you were chances are 1,000 years from now, when hopefully we will have solved that problem and brought the atmosphere back into a state in which we're likely to be able to survive the longer term. There's a good paper called Long-Term Observations. Jim Baker was the previous director of the NOAA. Carl Wunsch is a professor at MIT, and Ray Schmidt is a scientist at Woods Hole. And their observations, there is no global system of routinely funded long-term high-quality measurements to provide understanding of climate in general and the ocean in particular. So that's the now state today. Weather changes weekly, even annually, while climate changes over decades. And a reasonable time constant might be 30 years, the lifetime of this observatory. So it's essentially one cycle of change in terms of climate. And the fact that temperature or weather might change and become somewhat ameliorated this year compared to the year before is no indication that climate is doing the same thing. Weather is what happens, weather is what you understand, and through most of your lifetime, weather is what you will understand. Understanding climate requires this much, much longer term view of where we're going. We should be making observations over multiples of time constants. The time constant's 30 years. We know that it'll take 1,000 years, an eon, to actually clean the atmosphere of the greenhouse gases we have there today. And so you see that the number of cycles you have to make these observations over is huge. We need new institutions. We need to understand the impacts of climate mitigation. That is, how are we actually reducing CO2 when we take some action, cap and trade, for example? Do we know that actually is doing anything more than make people unhappy? Is it really reducing the carbon dioxide? It's kind of like the TSA, you know, they make you unhappy and not want to travel, but that's not what their point is supposed to be, and that's not what we're trying to do here. Is we're trying to make this thing work over centuries. Literature's full of tantalizing short records that don't illuminate at all the evolution of climate. Biological observations are very limited. No less than half of the global observation system is being funded today, and that's decreasing, particularly with satellites. And how can we convince government then to maintain a system of long-term measurements in an operational mode where properly calibrated observations are supported on a routine basis for the indefinite future? So this is a big elephant in anybody's room, and it's one we're dealing. Time's not on our side. Number of reasons here. I talked about that instrumental record in England is 349, now 350 years old. Atmospheric records have been kept since the Second World War. Ocean measurements began in the 90s. Ice measurements started about 5 years ago in the poles. Synoptic sea surface temperature began 30 years ago. The radar altimetry is 15 years old right now. And deep ocean physical measurements have only just begun. What's the temperature of the deep ocean? I came here then in 1972 to Scripps, and this is one of the examples that Scripps and UCSD are justifiably proud of, is Dave Keeling's measurements on Mauna Loa of carbon dioxide concentration. He started in 1957, and before that there wasn't any continuous measurements of CO2 in the atmosphere, and Dave had the fortitude and willingness to spend huge years in doing this, and today this is what the curve looks like. And as that has gone on, one of the things we certainly can say, because it was so well done, we can go back and understand very well how CO2 in the atmosphere has increased over time. We just don't have that kind of quality of measurements in nearly any other program. The Obama administration has promised to come to grips with climate change. The Copenhagen conference has obviously set some interesting goals. Maybe even the UN approach is not the suitable way to go about this. But we also know that the sea level rise and ice sheet melting has accelerated beyond the level that was predicted even at the last IPCC. It's one of the most phenomenal things that we have on Earth right now, is the rate at which ice is disappearing, and it's in an unprecedented rate, and you see that in the accelerated sea level rise. good questions of why. You've heard this one, Ronald Reagan, trust but verify, and how do you negotiate a treaty? There are a lot of similarities between treaties and climate change and past experience with arms control. You wanted to make sure people weren't actually building arms and testing arms, nuclear weaponry. You have to do the same thing with climate change. During the Copenhagen meeting, Ray Weiss had a quote that I just loved. It was having a climate treaty without verification is like going on a diet without a scale. And that's exactly the point. That's exactly the point. I mean, you have a feel-good treaty if you just say, yeah, we're going to reduce our carbon emissions by something or other. But unless you actually make measurements globally and understand that and try to understand how those policies are actually impacting Earth, then you're really not doing it. So you need to have this. You need to verify the treaty. And the Senate won't let you get away without doing that. There are a couple realities. Diplomacy will determine what can be agreed upon internationally, obviously. And politics will determine what can be tolerated domestically. So the scientist is left down here, what direct or indirect measures of measurement exist to track compliance and to measure trends. And so there are a lot of people here at Scripps and UCSD working on this. It's certainly something I'm working on today. Why do you do this? Where there's money, like cap and trade or taxes, there's dishonesty. And the propensity to cheat will grow in proportion to the economic stakes. I mean, this is just reality in a real world. So again, you have to think about verification. Monitoring is the provenance of scientists. We know how to do that stuff, ostensibly technicians and intelligence analysts. And verification is a political act. The president himself, herself, must assess whether the totality of information provides confidence that compliance is taking place. So that's a political decision. And you see a lot of political things and a little bit of science in here, but it's a critical part because it's that monitoring part. And it was that thing that was being written about in the emails in the Climategate here. That's what that person at NCAR was worrying about, is how do we build an observing system so we actually can determine on a shorter term basis how the planet is working. We need to measure climate on a global basis, and we have to understand when activities by parties to the agreement that violate its terms must be detectable in time to catch abuses before fruition. A lot of countries, China in particular, don't want to have a verification system, but there's no way we will have a treaty without that, I think. We have to derive the data from open source sensors like the system that I just talked to you about. Inspection systems that allow you to go on the site and evaluate things and deploy sensors even in a country. The poorest, least advanced party has to have access, and there must be confidence that the system will sustain treating monitoring requirements. Classified data are of utmost importance behind the scenes, particularly for the president, just as they are for arms control, and the transition of those data in classified systems is important. I have a thing here, Medea. Medea was on the front page of the New York Times last week, and it's a group of scientists, and I'm one of them, that works with intelligence agencies on understanding the data that they have and how that might be used in turn for civil issues of monitoring the climate. So it's a set of tools that we're not very familiar with generally, but an awful lot of this we've managed to declassify, in particular some of the really interesting, if you haven't seen it, there's some very interesting photographs of the Arctic that are available now for the last 15 years, and it's one of the longest, now becoming one of the longest term monitoring systems that we have, and they do it come hell or high water, day after day, year after year, and decade after decade. Treaty requirements, there'll be costs for environmental monitoring, and it'd be a waste of time to embark upon them until there was a plan for this. And then we have to ask, and we are asking, what parameters must be measured, with what degree of accuracy, to provide a data stream that improves our knowledge of climate dynamics and changes attributable to human intervention. And so that, we have to build a system to monitor the oceans and the atmosphere, land cover and so on, the poles, to a much more substantial level than we can do today in order to deal with this climate problem. Extensibility is important. I've talked about a number of features, and we've made this system that we're building, designed it to be extensible. And that means is that you can multiply the number of sensors in the field by 10, 100, 1,000, and the cost will go up at less than a linear rate. You don't have some kind of an exponential that's going to catch on and catch you in the end that will make this thing grow faster than just linearly. So extensibility is important, and one of the ways we've done this is by having the software systems all through the system work from the littlest thing near the sensor to the very largest thing sitting here on land. And the interaction, and no great surprise, you saw the Red Hat Linux. Red Hat's the supplier of the operating system. And really what we are building is an operating system for observatories. We can compile observatories from these sensors using these tools that we have. And our goal is to make access to Earth data and knowledge as simple as possible by hiding all the really complex stuff. So I put my title slide at the end here. This is me. And Nigella mentioned those things here. I'm primarily at the Institute of Geophysics and Planetary Physics. I was director there for 18 years, and I've always been based there. But I've also got affiliations with both Cal IT2 and the Supercomputer Center. And one of the things that kept me busy today was getting a proposal in for a new program to integrate all the very large-scale computing systems. I'm the PI for this thing in the U.S. that computed petaflop, 10 to the 12th floating point operations per second. That adds and subtracts. So that's a lot of calculations in a second. And we have several systems now in the US that will do that, but they're not integrated. They're not really available to people. And so our proposal, even larger than the one for the observations, went in at 7 o'clock this evening. And we'll see how that goes. There are two of us, two groups competing for this, and I hope we're successful for the observatories thing and being able to integrate data, real-time data into models and so on, being able to build the connections between all these things from the sensor clear to the large-scale computer that's going to deliver petabytes of data here that you're going to have to look at is very important in understanding climate. In 1987, when Steve Jobs came back to Apple, he got rid of most of the lines they were building and introduced a brand new one. And he really made a great leap at that time. He didn't ship the thing with a disk drive. It was the first one that didn't have a floppy drive. And the I in the iMac meant Internet Macintosh. And everybody thought he was crazy. But he never put a floppy disk on a computer again, and the computer itself was called iMac. So I've chosen iEarth, and its purpose, in a very short talk here, is determining the current and future states of Earth. And you can see the challenges that we have. I'm very excited about it. I think all the people working with me are. It's a great opportunity for me at this stage to be able to do something vastly different than I've done before. But it gives an opportunity to make a difference. And I'll look forward to your help and interest as the years go by. Thank you very much. Any questions? What new things are coming in? Well, one of the things that we have to do when we build a system like this is use materials that are available. We have to be able to buy them in a catalog, and so in a sense we're building a platform and a system here to bring things like temperature, wind speed, solar insolation at a site. I told you that biology was problematic, and it remains problematic, but has a great future. But the system, so we're measuring some of the things like you need to know. You need to know salinity. You need to know temperature in the oceans. We'll be able to make better estimates of the heat content of the oceans themselves. We'll make measurements of the deep ocean, which haven't been done on any regular basis in the so those are some of the new things, but we also, in the program, included autonomous vehicles carrying sensors as well, gliders and powered vehicles that we command through satellite. And they have fluorometers in here for making some rudimentary biological observations, but we look forward to the time and hope to increase the demand for the kinds of things that can make better chemical and better biological measurements. But the technologies for those are in their infancy, but there's some great possibilities in the future, particularly with now being able to barcode an organism through its DNA. So the hope is that through programs like this and the press and demand for making those kinds of measurements, even pH is difficult to make over remotely over a long length of time, and we need to be able to do that. So maybe it isn't too surprising, but I think one of the things that will be unusual and different is that you'll have them immediately. And as time goes on, we'll add new sensors that will make a big difference. Jules. The question was, how sustainable is this system? We know government is not particularly keep their eye on the ball on these long-term issues, and how about industry doing this? And I think industry is a real possibility. We're working with industry on this, and one of the things that I found I started the Southern California Coastal Ocean Observing System here, and one of the things that is most popular with industry are the wave measurements that are made by a program called CDIP. And they basically measure the direction and size of the waves. And there are two companies that actually take the data from this and resell it, repackage, resell it. And the biggest customer, of course, is surfers. And so the biggest user of these on a day in, day out basis are surfers. We have not had a model in the past for bringing some of that revenue back into the system, but it's the kind of thing in future you have to think about. When you think about things that are sustainable over decades and centuries, there are two things that come to mind. One of them is universities. Universities, some of them you can name, like Barcelona, have been around for almost a millennium. The other one that's been around even longer is the church. That's another long-term sustained system. And so both those organizations, both those approaches have many things to teach us about how you institutionalize a program like this in the long run. But it is a critical question. I'm not sure industry, because industry will be interested, but whether an industry will be able to supply the same thing for 100 years and return profits is unlikely. But having their involvement, having a revenue sharing system, intellectual property, and so on is something that we're definitely looking at as a source of support. This is an observation. What was the reason for it? And, the public has become more skeptical of climate change during the last year. There was an acceptance, say 2 years ago, in the order of 60%, and it's down to around 50% today. And there is a lot of information. Unfortunately, I think things like Climategate don't help at all when you have weeks of being inundated by the complete failure of climate scientists to understand what's going on, that it's just a hoax. The real reality is it hasn't changed the science at all, maybe illuminated some bad behavior on a few people's part, but it hasn't fundamentally changed the science or the directions we've headed in. But I think the perception in the population is that it's done great damage, and it's done great damage to the way people look at this, and is one of the reasons that I advocate, one of the reasons, not the only reason, but one of the reasons I advocate for openness of data, so that just not a few guys like me or my colleagues are the ones that are actually working with the data, but people that have a real interest and work on this as well. And maybe we can recover some of that, but we need to do a better job of dealing with stuff like Climategate than we did, because it hurt us a lot, even though, as I say, it didn't change the scientific picture at all. So scientists, I must say, aren't very good at this. Okay, thank you very much.